So first of all, let me thank the organizers for organizing this nice workshop, for bringing us all together here in Korea. It was long on my bucket list, so thanks a lot. And I've also, the short time I've been here, really enjoyed Korea, so I'm looking forward to a lot of discussions and the other talks. Before I start the talk, let me give a shout out to my amazing collaborators. Leo Bitussi, Gele Hatton, who is actually in the audience somewhere and is also giving a talk. Emil, who is also going to give a talk, Jörg Moseus, Jose Figueroa Ferrell, Alfredo Perez, and Alice Serraj. And there are, of course, these are the references this talk is based on, but there are many works that have been before this that have been very influential and important for this work, and all of them are fully cited correctly in our works. But during the talk, I have no citations, so please look at the references. And I prefer also to have maybe interactive talks. So if you have any questions or comments, and a lot of leaders and experts in the audience, please feel free to jump in at any time. I'm more than open to that. And otherwise, let's talk later. Okay, so the talk is roughly in 2 parts. The first is a little bit just a motivation about dipole moment conservation, which might not really be necessary for this audience, but maybe some of you haven't thought about this, so I still want to at least set the ground a little bit. And then I will talk a little bit about the Fracton infrared triangle and what that even is, which I guess not everybody will know at this point. Okay, so this talk is focused on particles and theories which have a conserved electric charge, and additionally also conserved dipole moment. So more precisely, this means we have angular momentum, which is conserved, or in the theories I'm looking at, energy, linear momentum, electric charge, and the dipole momentum. And what is not conserved necessarily is a center of mass conservation, which implies that there is also no boost symmetry that will generate it. And in this sense, the space-time symmetries are what sometimes is called Aristotelian. And if you look at the algebra of these charges, you see just the usual rotations. And as you could have expected, the 2 vectors are indeed vectors under rotations. But what makes this possibly interesting to study, but also has consequences, is this relationship, where one could think about it as a space-time symmetry that doesn't commute with an internal symmetry. And that is something that might be maybe unfamiliar for some of us. And this commute into the charge. And one way to think about this is by looking at this conservation law. And this conservation law implies a conserved charge, and also implies, by 2-time partial derivatives, that the dipole moment is conserved. And at least for me, I know dipole moment, but what is really different here is that the dipole moment is conserved. So we all know it from electrodynamics, but let me emphasize for those who don't know it, it's very weird that this is conserved. And the reason is, can easily be seen if you look, for example, at the isolated charge at the position ZT, and then this is the charge density. And if you impose that this that you have a conserved charge, indeed that is, just plug it in and the charge is conserved. But if you look at the dipole moment and you insist that the dipole moment is conserved, this implies that the position of this particle is not allowed to move. So this is what I would say a very drastic consequence of dipole conservation. And indeed, this is sometimes pictured like this, and this is actually something one knows from electrodynamics, that if you have a charged particle, then the dipole moment depends on the origin. So if you move it to the right, you have the dipole moment is non-zero, and if you insist on the conservation of dipole moment, then this is a process that is not allowed. This is again implies that the isolated charge is stuck to a point in this conservation. But what is interesting that, and that is again following from the same electrodynamics course, if you may, when the charge is non-zero, when the charge is zero, like in this case for dipole, then it doesn't depend on the origin anymore. And if you move both of them together to the right, the dipole moments of both of them add up to exactly the original dipole vector. And in this sense, dipoles can move as long as they move together and don't change the dipole momentum. So this is a process that is allowed now by this kind of systems with dipole momentum. And one question we were asking ourselves is, so we have some intuition now, if you like. So what particles with conserved dipole moment should behave like. So isolated charges are stuck to a point, but dipoles can move as long as they don't change the dipole moment. And what we were asking ourselves is there some action principle behind this kind of systems? And can we write them down? And for us, a little bit more theoretical, this is an interesting question from the perspective of elementary systems of the fracton and dipole. From the classical perspective, this is a question you could ask, what are the coadjuvant orbits of this group? Coadjuvant orbits are symplectic homogeneous manifolds on which this group acts transitively. But maybe what is better known, the quantum version of these elementary systems are just unitary irreducible representations. And the folklore is that these unitary irreducible representations in many cases are the quantization of this classical coadjuvant orbit. For example, if you do this for Poincaré group, and you look at the coadjuvant orbits and the unitary irreducible representations, you indeed find the particle actions you know from every book. And you indeed find the unitary irreducible representation that Igor proposed. So in this sense, this is an interesting question to ask what happens if you look at this kind of dipole systems. And in this sense, these are really elementary systems of this symmetry group. And what we have done, we took this fracton or dipole group and classified all coadjuvant orbits and unitary irreducible representations, and in this sense, classified the elementary systems. And for each of the system, we provided an action principle. The question, of course, now is, does this in any sense provide any relation to what I just showed you, or provides, fits together with the intuition we have? So let me just, I'm not showing you the full list of all the orbits, you can look them up, but let me just give you some kind of observations that follow from this classification. And the first is, you can see already by just looking at the symmetries that, again, this interesting commutation relation that the Q commutes with all other elements, and in this sense is a Casimir element, and is fixed on this coadjuvant orbits. And in this sense, if Q is zero or non-zero, are really two very different cases. And this is exactly the case when it's not equal to zero, we call it monopoles. And if it's zero and the dipole moment is unequal to zero, we call them elementary dipoles. And indeed, these are two different sectors just by the fact that this is a Casimir element, if you like. And on the way to operate this elementary system, one operates the action of the symmetries on this orbit. And a especially interesting part of this action is the action of the translation on the dipole moment. And indeed, what one finds is exactly what you would expect from the dipole moment. Under translation, the dipole moment changes in this way. And indeed, also what you can see by inspection, if the charge is zero, the dipole moment doesn't change. But if the charge is unequal to zero, the dipole moment is shifted. This is exactly in agreement with what I just showed you earlier. So indeed, I think that there is some relation between these elementary systems and the intuition we have for them. Yes? Ah, am I standing? You're seeing just half the talk. Should I start again? No, okay. All right. So, okay. So let me just maybe show you one of the actions, and it's embarrassingly simple if you like. If you look at the spinless monopole, which has charge non-zero, and you reduce the action and massage it a little bit, at the very end of the reduced phase space, you find this action, which is maybe one of the simplest actions you might have ever seen on a talk at a conference. But let me just emphasize that varying this with respect to pi really tells you that Q dot is zero. And this is exactly what you were hoping for. So it's really, and this is really just drops out, if you like, from book theory. So in this sense, it's really exactly what we were searching for. And maybe just some other observation is that there is indeed some kind of other cosmic element which is similar to what you call a spin. And indeed, this spin you can also like quantize it, and then it's really taking half integer values. So for these monopoles, there exists a generalization to higher spin. So maybe just as a summary, so if you want is asking the question, what is a fracton? One could ask, give the similar answer if you like, than Wigner gave. It could be seen as an elementary system of the fracton group. At least these monopoles have the properties you would expect. Let me maybe just, in passing, add a short comment that these fracton particles are related to another set of confusing particles, if you like, which are called Caro particles. And in that case, you just exchange the charge for the energy and the dipole moment for the center of mass. So you now have a center of mass conservation, but again, in a very interesting way, if you like. And basically everything I've just told you is equally true because it's just a matter of the underlying symmetries. And in this sense, this massive Caro particle, because this is not the relevant element of the energy, it's the mass, if you like, are stuck to a point for the same reason that monopoles are stuck to a point, due to the conservation now of the center of mass, and in the other case, due to the conservation of dipole. So at least I think the takeaway message is isolated monopoles are stuck to a point, but dipoles can move. So now with this motivation, if you like, we can move on and try to look at some of these consequences, at least in the way we looked at them. Which brings us to the Fracton infrared triangle. And as a first start, I want to explain to you what I mean by infrared triangle. I guess not everybody has heard about it, or has everybody heard about infrared triangle? Okay, let me spend a few words on that. I saw confused faces. All right. Okay, so what is the infrared triangle? Is actually a rather recent observation between three different effects, which is the memory effect, soft theorems, and asymptotic symmetries that have been studied for quite some time independently. But in recent years, it has become clear that they are related to each other in an interesting way. And what is interesting also that these insights from each of these fields have now helped the other field to make progress. And there have been interesting new developments on each of these columns. And maybe just to give you a short idea what the soft theorems are, for example. So this is a generic n+1 particle on-shell scattering amplitude. And there's the +1 is here a soft photon or graviton. And the interesting thing about the soft theorems is that the n+1 on-shell scattering amplitude factorizes if we send the energy to 0, which is the soft limit, if you like. And in that case, you can write this again as it factorizes here because now you have the soft factor and the amplitude without the soft particle. And in this case here, the pole and the other ones are subleading in the energy. What is interesting about this has been shown a long time ago, is that this is quite a universal formula, and it mainly depends on the fact that you have photons or gravitons, and nearly all the other elements of the theory drop basically out of this soft factor, as you can see. All that is nearly needed is the polarization and the momentum. And in this sense, this is quite a universal infrared effect, and is related to what has been recently shown asymptotic symmetries. So the soft theories can be seen as these ward identities of infinite dimensional asymptotic symmetries at null infinity. But null is meant from asymptotically flat spaces, if you send out radiation that ends up at null infinity, right? And these infinite dimensional symmetries are like enhanced infinite dimensional symmetries, for example, of the charge or inversion of the translations, which are super translations. And maybe the effect that has been, that is maybe the easiest to see or observe is the memory effect. And they come in two flavors, they look a little bit different for electrodynamics and for gravitation. But in that case, you have a field, a test particle, if you like, very far away, and the gravitation and the electromagnetic wave. And this electromagnetic wave gives a kick. But what is in the electromagnetic case? But there may be an interesting effect in GR. This is called a displacement memory effect, where you have two test particles very far away, and the gravitational wave passes. They oscillate. And what is interesting is when they settle down, they have a displacement with regard to the earlier position. And this is really a displacement that apparently will, at least is expected to be seen in the rather near future. So this is indeed an effect of general relativity that people, I think, from the LISA telescope guess that we will see the order of magnitude 5 years. But that is definitely an interesting effect. And as I said, they're all related to each other. But what all of I've just shown you, what they have together, what unifies them is that they're all based on theories that are Lorentz invariant. And also, these memory effects is quite a hard thing to measure with LISA, for example. And the question is, if this is a very robust structure, for example, you could ask, is Lorentz invariance one of the ingredients that is needed for this existence of these influence triangles? Or does all of this go away if we don't have a Lorentz invariant system? And suppose this is an effect that goes beyond the Lorentz symmetry, then it would, in principle, would be interesting if you could try to realize this in the lab and try to measure, for example, a memory effect in some kind of tabletop experiments. But first of all, I think the question we try to analyze is, does any of this still exist if you have a theory that is not based on the Lorentz invariant theory? So, what is the theory we looked at? Okay, let me make a short break and ask you, are there any questions at this point? Except that I'm maybe again standing in the way. Okay. So the theory we looked at is sometimes called a scalar charge gauge theory, which has the following action. And so there are two fields, and they're coupled to sources. And phi is just a scalar field, and Aij is a symmetric tensor, and there's a velocity c in this edge. And this theory has an electric and magnetic part. There are more general versions, but let not be restricted to this case. And they are given by these equations. And what is interesting is that this theory has the following gauge symmetry. And following from this gauge symmetry follows that you have this continuity equation for the sources. And this again is exactly the dipole conservation equation that I showed you at the very start. This is the reason why this is actually connected to the first part, if you like. And varying this action, you will find the following coupled equations of motion, which to some extent are, this is a little bit, for those who haven't seen it, is a little bit like a electrodynamic on steroids, if you like. And from these equations of motion, we now try to do a similar analysis to electromagnetism and GR, but we found various novel features. One of the things that we had to do is very often in the case of general relativity or in Lorentz invariant theories, one uses a specific coordinate system that is very well adapted to null radiation. But in that case, there's just one kind of null radiation, and that is very useful. But in this case, we will see that this is not an option anymore, so one has to do on a technical level different things. But in the following, let me say that I will mainly sketch what we did, and I will hide a lot of details and some things because there's quite some technicalities behind it. So don't look too carefully at all the formulas, but I think what I at least hope to convey is what we tried to do, what we set out to do, and how we did it roughly. But the details of each letter is maybe not too important. I hope at least that I can convey you what we tried to do. So what we tried to do is then what we want to do is to analyze the radiation. And in this case, of a moving dipole, and its effect on a dipole that is also moving very far away. And that is exactly the same thing that you do in electrodynamics if you look for the linear solution. But in this case, as we discussed earlier, rather than a monopole, you want to have dipoles because these are the elements that can move. So the source of the dipole linear solution is then a moving dipole. And in that case, you do the very same thing as you try to do in the case of electrodynamics. If you want to do this for the potentials, you gauge fix and try to decouple the equations of motion, which in that case is actually much trickier than in the case of electrodynamics. But in the very end, what one finds is two sets of equations, T is for transversal and TL is for transversal longitudinal, but that is not so important. What is important is that these are two wave operators, and both of them have unequal propagation speed. So this is something that you wouldn't find in a usual Lorentz invariant system because we propagate at the same speed of light. And that has quite a lot of interesting consequences, as I will try to explain in the next slides. So let me start by maybe describing the first thing that we did, which is really something very simple, if you like, is to do the same thing as you do for in electrodynamics. But in this case, the thing you should think about is, rather than having the usual linear solution, here you have now a dipole that is moving, so you have additional vector that you want to have. So you want to calculate the fields given some dipole that is freely moving. And for that, you need to define, tell you what the sources are here. And the sources are really given by this equation, which these two equations really fulfill that dipole conservation equation that I just showed you. Again, this is very much the same thing you do in electrodynamics, just a little bit more complicated. And what you then do is to solve these equations. And if you solve these equations, you find this one, and this is the analog of the linear solution. So if you see, this is the inversion, if you like, of the wave operator, and if you add this in here, you find that this equation, up to some projections you have to do, gives you the field in terms of gives you the field at any point in space given from the dipole that is freely moving. So that is very useful because actually a lot of what I'm going to do is based on this very, if you like, simple equation. Yes? And in this case, you put it in by hand already. So this is already for fixed DI. One can do it also dynamical, but DI is fixed at this point. I say this is not a dynamical thing, and it just moves along. But yeah, this is a good question, but one can, I think one can also try to do it dynamically, but in this case, it's just a constant that is fixed for the dipole.
You fix some gains. Did you do some fixing already?
Exactly, yes. The gauge fixing happens already at this point. It's the same as for the potentials in electrodynamics. Without gauge fixing, you couldn't do this. Because otherwise, A wouldn't be defined. Would have some gauge symmetries. Exactly. So, other questions? Okay, so we now have, in principle, up to some projections, the field at any point given some freely moving dipole. And now let's play with it. The first thing we want to do is to understand what the radiation of scattering dipoles, what happens to in that case. And so first of all, you have what we try to do is we want to think about this radiation very far away. And maybe the picture you should in general have in mind, give me 1 second, let's go there in a second. So we can just take these asymptotic fields, expand it in R, and look at the leading components of A. And then you find this. And in that case, we have set the speed also to constant. And the thing you have is, I think the picture you should, and now we want to scatter dipoles. And the picture you should maybe have in mind is you have some region, and you shoot in some dipoles, then something crazy happens, if you like, and then some dipoles leave again. And given this crazy interaction, if you like, there's some fractonic waves going out, but there are two radiation regimes because we have two different speeds. So you have radiation, so they're like they decouple if you go very far away. And from the scattering process, this induces now what people call a memory. And that is really just this quantity, which is the difference between the fields in the very far region. And you have two of them. And if you add them up for all these dipoles, you find the following, what is called a memory effect. And what is maybe interesting to see is that this is actually one could call already a memory effect. And what is interesting that this is a very simple actually quantity, and it's only dependent on the speeds at the very end, at the very start. And as I say, that you set them to constant because if you go very far to the past, you would need infinite energy if they would all the time be accelerated. And one thing you can do now is to ask what is the effect of this change in the fields that is very far away on a test dipole that sits here in these far regions. And the dipole is affected by the radiation by some kind of generalized Lorentz force law. And this can be found to be of this form. And now it uses the asymptotic form of these fields and tries to look at what the change of the speed of this dipole that is moving here in the far region is. And besides the details of this formula, the thing that is interesting is that both of them contribute. So the TL and the T component both give a change to the speed of this dipole that is moving in the very far region. So one gets both from the fast and the slow radiative modes some kind of kick effect on this test dipole. And that's the reason we call it double kick effect. So let me maybe just show you some formulas. So again, as I said, there are like two different kind of waves and two different wave regions. And in this sense, this is very different to null infinity, where you have just one region where everything ends up in. In this case, when you go very far away, you to decouple. And there are actually some quite interesting questions hiding in there that also conceptually what goes beyond what people might be wondering about in GR, for example. But if you have a dipole in this far region, then this dipole gets two kicks, first from the fast and then from the slow radiation. And in general, this fits quite well with the soft theorems and asymptotic symmetries. So let me just add a few comments on the asymptotic symmetry part. Forget the technical details, but let me just try to convey you what's happening there. So one gets, again, similarly to electrodynamic and GR, an enhancement of the symmetries. And in this case, one has still a charge, but one has enhancement, for example, of the dipole charge, which is an infinite dimensional enhancement. And you get two of them in each charge sector. But what is interesting, the L1 mode is exactly the old dipole moment that you already knew. What is maybe more transparent, I guess, is that as soon as you have these conserved charges, but as soon as you have radiation leaving the radiation region, these charges shouldn't be conserved anymore. And what one finds indeed for this theory is that this is true, and you get some kind of flux balance equation, which tells you that the charge has to change with the radiation that is leaving. And you get something like this for each of these two regions. And similarly, even I guess more transparent is that this radiation also carries energy, and this carries energy away from the system. So this system has this energy and obeys this conservation equation. And just inserting this asymptotic fields, one finds actually, I think, something quite neat. One finds that the energy in time changes according to the following rule. And what is nice to see is that this quadratic quantities and that there is a minus sign, which means that the energy is always reducing by the fact that the energy is going out. So this, I think, comparably, at least for me as a theoretician, this is quite a physical thing. that is happening. And it's actually quite similar to what happens in GR. So to some extent, this is the fractonic analog of Bondi's energy loss formula. Yeah, radiation always carries away energy and reduces the energy of the system. Okay. Are there any questions at this point? Yes.
So imagine you take like two dislocations, you try to scatter them. What would be like the experimental kind of intuition about what you're like?
So did I understand correctly? Dislocations? So you mean like you mean like where we just I'm sure I understand the question. You mean like you do this elasticity, fracton duality, and then you mean the defects there, or what do you mean by dislocation? Just to be
It's like sources of like dipole symmetry, like elasticity.
Okay. So okay. Good question. I mean, I haven't thought, to be honest, I have stayed completely, I mean, that is one of the things you wanted to think about, but you have completely stayed in the fractonic world and not dualized to this elasticity story. But I feel like this is actually one of the questions, to some extent, we are still wondering about, and actually that I thought I asked the people here who are much more experts on this elasticity story, because I agree with you, this is possibly a much more physical system for this, what can be seen more as a proof of concept, if you like. And I feel like, yeah, maybe this, I would love to hear the answer to that. But I don't know. I mean, I can tell you what happens in the dipole case, but whatever happens if you dualize it, but I haven't done this, so I don't know.
What would be like B+1, right?
So I guess you're working 2+1.
Yes, yeah.
So I guess like
yeah.
the relevant answer for Piotr's question would be like in 2+1 dimensions. Because
Yeah, no.
so at this location is a dipole. So what you are saying somehow, what you are doing would be applicable for elasticity, but if you were like in 2+1.
Yeah, so in principle, I mean, one would need to work it out, but conceptually, okay, there's some subtlety always with going to even odd dimensions. So I mean, I feel like conceptually, I think that one could try to do the same thing in 2+1 dimensions, and one could hope for it to translate to some extent. But I agree. I mean, 2+1 dimensions is has some subtleties to it. But I think that finally this is one of the things that we have on the to-do list, but haven't done it yet. But it's 2+1 dimensions often is a little bit tricky, at least in the GR case, and because the IR divergences get worse rather than better. So there, it's hard to say something precise without sitting down and doing the work. But I feel like at least conceptually, I think one could try to do it, and I would expect something to be there.
I have a question about infinity. So in the standard Lorentzian case, they have light cones, they have a speed of light, and the speed of light defines your future null infinity in some sense. But here you seem to have like a dispersion relation dependent notion of infinity, so different modes have different speeds and so you have different motions of infinity. It's a bit similar to like what happens in horizontal redshift gravity, where you have black holes with dispersion relation dependent horizons. But you may still wonder if there is a universal notion of infinity, that at the end of the day, everybody ends up with some universal infinity. Do you have a geometrical understanding of what you mean by infinity?
Okay, I haven't thought about it from this perspective. I would somehow not expect a universal infinity, right? Because I mean, suppose this radiation will never hit this radiation, at least from my understanding. But
it's an Aristotelian space.
Okay.
So there must be some notion of infinity associated. At least
yeah, I feel like,
have you thought about that?
No, yeah, okay. What we thought about a lot actually is because it's an interesting question is what happens in between here. I think like this is maybe the same question that you're asking, like because if you go very far in U, because to some extent if you like, this is U to infinity, and this is in this direction is U tilde to minus infinity. And at some point, the question is how do they meet and do they meet?
But does it even clearly have differences? Like, you know, if for asymptotically flat space, you would have spatial infinity, null infinity, all that.
Yeah.
Is it clear that you have similar kinds of infinities? Because those are light
I think I'm pretty convinced that the phase spaces decouple in this very far regions.
Okay.
Yeah, I think that is pretty clear. But as soon as you go a little bit in the inside, and that at some point you need to ask somehow you would like to match them, I guess.
But it's still an action-dependent notion of infinity. Because if I write down different action, I get different speeds, and then we get different notions of infinity.
Yeah, it's a good question. I mean, we have thought a lot about it. I thought like if the speeds are indifferent and you go far enough away, that it is decoupled. But you can always ask, what if I don't go infinite far away? Then all of it is much more complicated. To some extent, this a lot of what I'm saying is, of course, based on the fact that you go very far away and this basically decouples. But it's a good question. I think that the general picture of that, at least, we haven't fully worked out. But I feel like that for practical purposes, that I think these phase spaces decouple if you go far away.
Because you might wonder if it's robust to like corrections. If you add other interactions to your theory, your notion of infinity might correspondingly also change. Because the speeds here are the properties of your theory, not of the geometry.
It's a good question, yeah. So you're saying, yeah, I mean, okay. So you're saying it could happen that the speeds are the same. I mean, I feel like as long as they're different, we would have different variations on it. But I agree, I mean, I'm definitely open to even crazier possibilities. I mean, but already not going to more to this maybe more complicated scenarios, just going to more finite, not going that far out, even like already there is a much more tricky situation happening. So there's a lot to be explored, and a lot of these questions don't arise that naturally in a Lorentz invariant setup, which could make it possibly interesting. Or but I agree, fair point. I mean, we have thought a lot about it, but I think I don't have something extremely robust to say at this point.
Thank you.
Okay, any more questions?
Sorry, I missed the first part of the talks. And usually the soft theorem or factorizing theorem is useful for removing the infrared divergence which appears in the quantum field theory. In this case, it is also such kind of thing happens. For example, this soft photon for the dipole scattering, and it can play the role of some kind of a regularizer or of the infrared physics.
Okay, good point. So let me show you what happens. Then maybe you can answer yourself. But I mean, so, let's say there is again something very similar happens. So the dipole soft theorem. So you can make now a scattering process with n dipoles, and at the emission of a fractonic soft photon, similar to the case that I just showed you for electrodynamics and GR. And now the scattering amplitude is again expected to factorize. And again, as you said, this dipole I think you're talking about is exactly this pole here, omega, which you can set to 0. And indeed, this happens. I mean, we even show it for some kind of effective model of dipoles, which in the end shouldn't matter too much. But using this, and for the soft tractor, one needs to introduce some external soft photon into the hard process. And this is indeed similar to adding additional hard particle propagator in the vertex. The details don't matter too much, but in the very end, you indeed find one of these soft factors. And if you project this and add up all the n particles you had at the very start, you find these two soft factors where there is a 1 over omega in front of them. So this is really the dipole analog of the soft factors you had in electrodynamics and then general relativity. And again, it follows the very same rhythm that you have a 1 over omega. And it also agrees nicely with the memory effect. So what I showed you now mainly was like they're like independent derivation of each of the phenomena. But we also showed that they are actually really connected, which I, for the sake of time, couldn't show you. But for the case, this is maybe the closest you can think about it. If you remember the formulas for the memories, this is really very much the same formula. It's a Fourier transform between them. And again, it mainly depends only on the initial and final velocity, which somehow, again, in the details of the action that I just showed you completely dropped out. So this is again like a very universal thing. And so let me just sum up. And so what I showed you now is like the Fracton infinite triangle, if you like, with a double kick memory effect, some dipoles of theorem and asymptotic symmetries. And to my knowledge, is the first realization of this kind of connections beyond Lorentz symmetry. And I think this shows that this is a robust structure. And indeed, I think this is interesting to further explore. For example, in this 2 + 1 dimensional case, I think this is more like a proof of concept that this can even exist beyond that. And I think it's a rather rich world because it's due to the fact that Lorentz invariant doesn't impose the restrictions you usually have. You get some new effects that couldn't happen in the Lorentz invariant symmetry, similar to constant bosons where Lorentz invariance is rather restrictive. So one of the open questions, of course, can this double kick memory effect be measured? And I hope some ingenious experimenter could realize the system and show it. But possibly this is more like a proof of concept and shows that these IR effects exist beyond Lorentz symmetry. And indeed, one of the systems we were thinking about where this could be maybe closer related is exactly this duality to this elasticity models where one could hope for closer to experiment effects. But indeed, this opens the door to explore this inferred structure for other models of relevance. So in the end, I thought I'd finish with a question. Because I think we now have the tools, and I think we see now that these ones are somehow interesting. Are there other theories which have propagating, gapless propagating degrees of freedom, which seems to be one of the requirements for these relations that we, I think, really need to show them, which has a lot of great experimental control. And if yes, please come to me and tell me about it. And because it could be interesting to explore these infrared triangles in other models which are closer to experiment. And in principle, the measurement of the memory effect is still an open point. So I would be very curious to hear about it if you could, in principle, realize this in a condensed matter system. So thank you.
Yeah, thanks. So I have a question. So we begin with scalar chart theory.
Yeah.
But then when you show us intuition, I look like you use the vector chart picture to.
When I should what?
When you use intuitive picture to derive the kick and memory effect, it looks like you use a vector chart. Right, because you're saying that your particle has the dipole from the beginning. At least when I see your picture, like
This one?
yeah. Or you think can like begin from your scalar chart.
I think that, at least to me, this is the picture for the scalar charges.
So in this picture, how do you derive the C tilde from the beginning? If you begin with the scalar chart theory with only one vector, one velocity system, how you derive the C tilde?
I mean, the C tilde derives. So this is the scalar charge theory.
Yes.
And the C tilde derives from the fact that you make a mode decomposition, if you like, of this field. Or in other words, if you like, this derives from the fact that we gauge fix in a nice way to decouple these equations of motion. I mean, I agree this is a non-trivial process that I haven't shown here at all because it's a little bit tricky. But in the decoupled case, it comes from the fact that you decouple the modes, and the modes have different speeds of propagations. Also really for the scalar charge theory. You can show this simpler by just looking at a mode decomposition.
Okay, thank you.
Okay, sorry.
for the sake of time, I think we better move on. You can ask questions.
I'm around. Thank you.